Hello, my name is Soumya. I'm here with my teammates Shruti and Roshni. Together, we are here to present our project SafeClick, anti-phishing measures for enhanced cybersecurity protection. Here's the outline of our project. In the introduction, we'll explain what is phishing and the challenges it creates, and how our project SafeClick helps to overcome those issues. And the related work will discuss about the older techniques like blacklists and the heuristic-based systems, and explain why our machine learning approach is much more effective than those techniques. Coming to the proposed work, we'll provide an overview of an application, including how we reprocess the data and how we extract the key features and how we implement the machine learning models and their evaluation. And we talk about the system architecture and the UI, and also demonstrate how our project works with the demo screenshots. And finally, we conclude our project and also what future work can be done. Coming to the introduction, let's talk about the problem statement. Phishing attacks mimic legitimate websites to steal sensitive data. Phishing is a very common online attack nowadays, where hackers trick people into sharing private information by creating fake websites that look very real. Coming to the challenges in the existing system, limited adaptability to evolving threats. For example, if a phishing website changes its domain or design, the traditional systems fail to detect those because they depend upon the fixed patterns. Coming to the next one, poor interpretability reduces users' trust. Imagine if a system alerts you about the phishing site, which doesn't explain you why the site is dangerous. So, without a clear explanation, user might not trust the system or take it seriously. Coming to the third one, inefficient in computational resource usage. Some systems take too long or require too many resources to analyze the URLs, which makes them slow and impractical for the real-time use. Coming to the goal of our project, SafeClick fixes all those challenges, and it uses a machine learning approach to give the accurate results, which also predicts like the real time. It gives the real time predictions and also tells why a URL is a flagged, flagged or the safe one, and also which helps the users to trust it and understand the system. Coming to the related work, phishing detection has been evolved over the years. So, starting with the traditional methods like blacklists and heuristics, let's talk about the blacklists. Blacklists are the list of websites that are already known to be dangerous or very bad for the phishing. If a user tries to visit one of those websites or the URLs, the system blocks or alerts them. However, blacklists have a limitation that they can only stop the websites that are already identified as bad, but not the new modified ones. Coming to the the heuristic based systems, they use a set of predefined rules to identify the phishing websites. For example, they might check if a website has a suspicious URL or uses any strange characters in the URL in the unusual ways. They often fail when attackers create a new tricks that that are which don't match with the old existing rules. So both of these methods work up to some extent, but struggle to keep up with the constant changing tactics of the phishing attackers. Advancements in the machine learning. So machine learning has been improved phishing detection by using the features by categorizing them into structural, content based, and the behavioral features. And also, however, it has been improved in the detection of the phishing URLs. It has some challenges to it, like how to scale the systems to the large uh, amounts of data, and also making the systems transparent to the users, and also ensuring it works efficiently without heavy computational costs. So, our SafeClick project improves those existing methods by using feature selection methods like recursive feature elimination with cross validation and also correlation matrix to select the relevant features dynamically, ensuring the better performance and also better detection. Coming to the proposed work. Now let's see the application overview. Uh, Coming to the front end, it is a simple UI built with the HTML and CSS for the users to give the URLs or the websites uh, and to check if they are safe for phishing. Coming to the backend, here pre-processing of the data is done, basically preparing the data for the analysis, and then the modeling is done by using the 5 models, which tells us to classify whether they are safe or phishing URLs, and finally displaying the results to the user in the real time. Coming to the dataset and pre-processing, in the dataset overview, we have a dataset with the 10,000 rows initially. We have reduced it to 9,581 rows after pre-processing. And also it has 49 features initially. We have reduced it to 37 after feature selection. And also we have a balanced dataset with the equal number of phishing and legitimate samples. The features has been divided into 3 types: structural features, content features, and the behavioral features. Structural features. These features are related to the structure of the URL, like num dots, and the host name length, num dots. This is a feature which counts the number of dots in the URL. If the phishing sites often use an unusual number of dots in the domain name to confuse users, which makes the site look like legitimate. For example, if a URL like www.bank-secure-login.com may have more dots than a typical website, it's signaling a possible phishing attempt. So coming to the hostname length, the feature measures the length of the hostname, like we'll see with the example www.example.com. Phishing sites may use the longer or oddly structured host names to trick the users that they are visiting a legal website. Now coming to the content features, these are based upon the content of the website, such as PCT, EXT hyperlinks, and num sensitive words. Now let's see about the PCT EXT hyperlinks. This feature measures the percentage of the links on the websites that leads to external sites. Phishing websites often contain a higher percentage of external links, which use to redirect the users to malicious pages or trick them that they're thinking they're on the legal page. For example, a legitimate bank website will mostly link to its own pages, but a phishing website might link to suspicious external domains. Coming to the num-sensitive words, this feature counts the number of suspicious words or sensitive words like login, bank, security, etc. The phishing websites often use this type of words to create a sense of urgency or to trick the users into sharing their personal information. If the site contains many of these words, they're trying to deceive the users into thinking that they're on the trusted site. Coming to the behavioral features, it focuses on how the website behaves. For example, iframe or the frame checks if the site loads the content from the other domains, which is common in the phishing sites. And coming to the submit info to email, uh, it is a feature. It looks for the forms on the website that sends the data directly to an email address, a typical sign of phishing attempts to steal the personal information. But a legitimate website doesn't do that because it uses a uh, like secured forms, like to send the data directly to their websites. So coming to the pre-processing steps, we have cleaned the data by removing 419 duplicate rows to avoid the repeated information. And also we have handled the outliers by removing the extreme values, like URLs with more than 20 dots, because they're very extreme. And then we have removed irrelevant features like ID and HTTPS in host name uh, because they don't add any value for prediction. Finally, we have normalized the numeric numbers to make sure they're on the same scale, making the data easier for the data modeling, uh, making the uh, making the data easier for the modeling process. And this slide shows you about the data set has equal number of legitimate class sample and the phishing class sample. Basically, it is a balanced data set which helps the model work more better. So, further, how is modeling is applied on the data and how the evaluation is done is explained by my teammate Shruti. Thank you.
Before diving into the models, let me walk you through how we prepared the features for our models. In machine learning, the quality of input features plays a critical role in determining the performance of the model. So, to optimize this, we used a combination of methods to select the most relevant features while eliminating redundancy and noise. Our primary method for feature selection was recursive feature elimination with cross validation, which is also called as RFECV. This method works by iteratively removing the least important features and evaluating the model's performance at each step. The process continues until it meets the shopping condition, which is maximizing the cross validation score. To determine feature importance during the process, we use random forest. This approach allowed us to systematically reduce the original 49 features to 37, all without compromising the model's performance. To complement RFECV, we also conducted a correlation analysis to identify and remove features that were highly correlated with one another. Highly correlated features often contribute redundant information, which can unnecessarily complicate the model and degrade performance. For example, we found that certain structural features like num dots and host name length were both highly predictive of phishing and minimally correlated with other features. This made them strong candidates to retain in our final feature set. By removing redundancies, we ensure that the model remained efficient and focused. In addition, we also calculated the feature importance scores using random forest. These scores provide a clear ranking of which feature has the greatest impact on classification. Here, for example, feature like PCT external hyperlinks, which measures the proportion of external hyperlinks in a URL, and num-sensitive words, which count words often associated with phishing, stood out as critical indicators for distinguishing feature URLs from legitimate ones. This combined approach of RFECV, correlation analysis, and feature importance ranking allowed us to build a refined, streamlined, and interpretable feature set that set the stage for the next step, which is the main modeling implementation. Here, we used 5 models. The first model we implemented was the decision tree. Decision tree worked like a flowchart where the data is split at each node based on a specific condition. For example, if you take this project, the one condition might be, does the URL contain more than 3 dots? And there are many more conditions like this. These split are guided by metrics like the Gini index, which measure how pure or homogeneous each node is after splitting. The process continues until the data reaches the leaves, which represent the final class levels such as phishing or legitimate. Decision trees are straightforward, interpretable, and good a baseline for more complex model. Building on this, we implemented random forest, which takes the concept of decision tree to the next level. Here, instead of using a single tree, it generates multiple decision trees, each trained on a random subset of the data. The prediction of these trees are then aggregated, usually through a majority vote. This ensemble approach improves accuracy and robustness, making random forest highly effective for capturing complex patterns in the data. Next, we explored gradient boosting, another ensemble method, but with a sequential learning strategy. In gradient boosting, each tree is built to correct the errors made by the previous one. For example, if the phishing URL is misclassified in the first tree, The next we will focus on the specific mistake, gradually improving the model's overall predictions. This iterative process allows gradient boosting to capture subtle relationships in the data. It was our top performing model, achieving an impressive accuracy of 98%. We also evaluated the SVM, which is the support vector machine, which is particularly effective for dataset with complex boundaries. SVM works by finding the optimal hyperplane that separates the two classes, in this case, phishing and legitimate URLs. What's unique about SVM is that it maximizes the distance or margin between the closest points of the two classes, ensuring a robust decision boundary. Additionally, it can use kernels to map the data into higher dimensions, make it flexible for more complicated patterns. Lastly, we implemented KNN, which is K nearest neighbor, a simple yet intuitive model. KNN classifies a data point by looking at the closest K neighbors and assign the majority class among them. For example, if 3 out of 5 neighbors of the URL are phishing, KNN will classify it as phishing. While it is computationally expensive for larger data sets, it served as a helpful baseline for comparison. Once these models are implemented, the next step was to fine-tune their hyperparameters to maximize the performance. Here, hyperparameters tuning is like adjusting the setting of a machine to get the best output. Here we use rich search cross-validation to systematically test combinations of hyperparameters and identify optimal settings for each model. Let me share a few examples. For random forest, we tuned the number of trees and their maximum depth. This allowed us to balance model complexity and performance. Too few trees might underfit the data, while too many could lead to overfitting. In gradient boosting, we adjusted parameters like the learning rate and the number of estimators. The learning rate controls how much the model learns with each step, and the number of estimators determines how many sequential trees are built. Tuning these ensures the model learned efficiently without overfitting. For SVM, we experimented with different kernels such as linear and radial basis function, as well as regularization parameters, which control the trade-off between achieving a low error rate on the training data and maintaining a simple decision boundary. We used phi-cross validation during the process to ensure the tuned hyperparameters generalized well to unseen data. By splitting the data into 5 subsets and the training the model on 4 while validating on the fifth, we minimize the impact of data variability and ensure robust performance. So the next will be continued by our teammate Roshni.
So, hi everyone, this is Roshni. So, let me go through the performance metrics. So, basically, we perform various metrics, that is accuracy, F1 score, ROC, AUC. Let me give some brief explanation about each. That is, accuracy means proportion of correct predictions out of total predictions, whereas F1 score means harmonic mean of precision and recall. It emphasizes balance between false positives and false negatives. And ROC AUC, that is receiver operating characteristics area under curve, evaluates models' ability to distinguish classes by considering all classification thresholds. So we perform this metrics, all three metrics, and we ended up getting best results with accuracy. What could be the reason why we ended up getting accuracy as our best result is because of our data set. Uh, the data set is balanced. Why? What is the reason behind that is because we have equal number of phishing and lynchment samples. If you can see here from this visualization, there are equal number of phishing and like lynchment data. So that means that is a balanced data set. So since accuracy is more reliable because of it on the balanced data, whereas FN scores and ROCUCs are perform better in imbalanced data. So we selected accuracy as our performance metric. Now let me go through with the model selections. So we performed like 5 different models as Shruti said. We performed random forest, decision tree, KNN, SVM, gradient boosting. So among this five, we ended up getting gradient boosting and random forest as our top models. We even perform statistical validations, that is t-test, on average, like we performed on average accuracy across 5 folds. So what do you mean by this t-test? So t-test is a statistical method which is used to determine if there is any significant difference between two groups. That means significant difference between the mean of two groups to be exact. So with the help of this t-test, we could able to compare different models, and statistically we could get we decided gradient boosting as our best model. So if you can see this, these are our t-test results. So what does this mean? If the p-value is less than 0.05, it means there is a significant difference and it rejects the null hypothesis. For example, if you consider this SVM and KNN, so it's like 0.32, which is greater than 0.05. That means there is no significant difference between this both models. So we can straight away take this out of our list and considering as a top model. Whereas if you can see others are greater than 0.05, for example, this is like to the power minus 0.7. It means like very minimal value, so we can consider them. So what does, okay, now you understood about p-value. Now what does this t-statistics mean? T-statistics means that if there is a negative value, the model 2 outperforms the model 1. In this case, let's say random forest outperforms the decision tree, whereas here gradient boost outperforms the decision tree, whereas in this case, gradient boost outperforms random forest as well. That's how we ended up concluding, though the top models are gradient boosting and random forest, among these two as well with the statistically test validation, and with the high accuracy we consider for our deployment gradient boosting as our best model, since it has a very strong ability to even capture complex patterns as well. So since you now understood about our model, so let me give you a brief overview of our system architecture looks. That is the front end and back end. It's a simple UI with basic HTML and CSS, and backend is like we used Python for the model evaluation and all, and Django framework to connect the UI and our backend. So I'll give a simple user flow so that you'll understand what exactly is happening behind the scenes. So in like this is the in front scene, so you give an URL. So behind the scenes, the feature extractions will be happening and the models are classified. So with the help of the models, so it will classify either into a safe or unsafe URL. That's how you'll get a result on the front end. So I want to now show our application so in a real time so you can understand how exactly it looks. So these are like some of our demo screenshots. This is how our application looks, but still I will go through our with the my application itself. Our application itself. I hope you can see this is our application. So to run this, Python manage dot py run server. This is the command which we use to run the application. So once you run the application, so you will ended up with this URL. So when you click this, so this what happens. This directs to our application. So this is our main page. Let me give an save URL. So when you click on a check, it gives a message saying that the URL is safe and legitimate. The reason why, because this is a Google URL which I gave. It has an HTTPS and www. Let me give an unsafe URL, for example, this. This is unsafe. Let's know what is the reason for it. You can click on more info. So there is no HTTPS and it has a sensitive words like login, account, which makes it more suspicious. We wanted to even include best practices so that the user will understand like or take some precautions to avoid some of the phishing websites. Let me even check another unsafe URL. Suppose I give a random URL. Let's say what does it gives? Okay, it gave me there is no HTTPS. Yes, it's correct. And I did give a random URL. That's what it even saying. Random host name saying that URL host name appears random, which is a common phishing attack. So that's how we could able to give some such piece like warning. It not only like detects whether it's unsafe or not, with it even with the help of the more info we can know what is the reason why the URL is phishing or not. So this is about our simply about our website. So let me conclude. So as I said, like we ended up with gradient boosting as our best model, and we use feature selections as RFECV as our feature selection to enhance more efficiency. So we want in our future, like our future work could mostly be focusing on advancing the hypertuning and enhancing the efficiency of our models further and try to implement any real-time phishing alerts to browser extensions and integrate domain reputation checks and IP analysis. That's what we are planning about in our future. So that's about our safe click. Thank you.